Hi student, in this video we are going to discuss some questions based on motional EMF. Here the question we have is, there are two conducting rails placed horizontally. These two conducting rails placed horizontally at a separation D in a vertical magnetic field. In a vertical magnetic field they are placed. These two rails are joined by a resistance R, and there is a movable conducting rod of length D, mass M, which is going to slide on the rails, on the horizontal rails, with the help of a constant force F. A constant force is acting on the rod, and we have to find the velocity of this movable rod as a function of time. We have to find the velocity of this rod as a function of time. And it is also mentioned that initial velocity is 0. Initial velocity is 0. So how to proceed this type of question, I am going to tell you. Now, because of the motion, this force, it will start moving and it will acquire some velocity. This conducting rod will acquire some velocity. Let us say at any time t, its velocity is v. Then this conducting rod is moving with velocity v in a magnetic field which is perpendicular to it. Because of that, an EMF will develop, and that EMF develop is BVL, and the upper polarity will be, by using the right hand thumb rule number 3, we can find what is the polarity. So this rod AB has been replaced by this particular battery. Conducting rods are not having any resistance, and this resistance R is there. So by using the KVL, we can say, let us say current I is flowing, then I will come BVL by R. Here D given, I am writing it L. BVL by R. Now this current is varying with time, because we are taking velocity at any time t. Any time t. Now because of this current, this rod AB will experience a magnetic force. We have seen a current carrying conductor experiences a magnetic force. This will experience the magnetic force in this direction, F magnetic, and this magnetic force will come out to be IBL, that is, it will become B square L square V by R. The magnetic force comes. So if we draw the free body diagram of this movable conducting rod, then on this two forces are acting. One is the constant external force which is mentioned in the question, and one is the magnetic force which we got this value, B square L square V by R. And under the action of these two forces, it is having some acceleration A. So if we write the Newton's second law equation for this conducting rod, then it is going to have the acceleration F minus Fm is equal to m into acceleration, which we can write as F is constant force F minus B square L square V by R. So I am writing B square L square upon R as alpha. Alpha V is equal to m dV by dt, where alpha is equal to B square L square upon R. Now this equation we can write dV upon F minus alpha V is equal to dt by m, dt by m. So it will give you, integrate this equation, f minus alpha v equal to integral of dt by m at t equal to 0, velocity was given as 0, at any time t v. Solving this equation you will get v as a function of, right? So once again I am summarizing. Because of the force, this conductor will acquire a velocity. Because of the velocity moving in magnetic field, EMF developed. Because of that EMF, current is flowing. Because of that current carrying wire experiences a magnetic force. It experiences a magnetic force. Under the action of this force and the magnetic force, applied force and magnetic force, it is moving. Then we have to write the NLM equation and then a little basic mathematics to reach to this particular part. It is very conventional questions, but they are important also. This is, I will say, with respect to JEE Main, they are little higher level, but with the help of one question, you can learn many concepts. In that way, it is going to help. Take the next question. This question is also something similar, only the initial conditions might be different. Here two conducting rails, same way like in the earlier question, placed in a vertical magnetic field, smooth only, no friction anywhere. The two rails are joined by a resistor. This movable conductor is moving with velocity v0. Now in the previous question, that was moving with the help of constant force. Now here it is moving, it is given some velocity initially u0, and after that you have to find the velocity as a function of time and the current as a function of time. Now let us say it is having the velocity v at any time t. This conducting rod is having the velocity v at any time t, and at this time only I is the current in the circuit. I is current in the circuit at this moment only. So if this will be the case, then as this conducting rod is moving in magnetic field, it can be replaced by a battery because an EMF induced in this BVT, and because of that a current is going to flow in the circuit, let us say I. Then just like in the previous question, I is equal to BVD upon R. Because of this current, a magnetic force is experienced by the moving rod. It will be Fm, and Fm will be equal to IBD, that is B square D square V by R. Now same concept like earlier. Now under the action of this magnetic force, it is moving. So if I take this rod free body diagram, its velocity is V, magnetic force is acting in this direction, so it will have the acceleration in this direction, so the speed is going to decrease with time. So if we write the equation, we have to write Fm is equal to minus m dv by dt. This minus sign is kept because dv by dt is negative. So Fm comes, I am writing b square d square by r as some constant. Alpha v is equal to minus m dv by dt. dv by v is equal to minus dt by alpha dt by m. Integrate. At t equal to 0, the velocity is v0. At any time t, v. By solving this equation, you will get v as a function of time. Once you have the velocity as a function of time, you can make use of this equation to get the current as a function of time. Again, the same thing. Here, force was there which is imparting some velocity. Here, already some force is velocity is there which is imparting the magnetic force, EMF, etc. and then the speed is changing with time. Take next question. In this question, it is very nice question, seems to be little lengthy, but it will be solved only in one statement, one line. Same arrangement like in the first question, but here they are asking find the steady state speed. Steady state speed means constant speed. And when the particle, any object moves with constant speed, when the acceleration is zero. When the acceleration is zero. If you recollect the first question, its acceleration is given by F minus Fm equal to mass times acceleration. So when the acceleration is zero, at that moment, what is the speed? That will be the steady state speed. The speed at which the acceleration is zero is the steady state speed or the terminal velocity also you can call it. So for A equal to 0, you will get F equal to Fm. Now I am writing the Fm from the previous thing. F equal to IBL, I was BVL, here D upon R into BD. This comes. So your steady state speed comes out to be F into resistance R upon V square D square. This is your steady state speed. I will just slide the screen. You can see the magnetic force was this value, right? So we have taken that. This is the steady state speed. Now take one more question. Now in this question, what is happening? We have one conducting rod AB which is rotating with angular velocity omega about one of its end in a uniform magnetic field. In a uniform magnetic field. And we have to find the EMF induced across AB. We have to find the EMF induced across AB. Right? So how to proceed this type of question? Now here if you see, if it is moving with angular velocity omega, if this rod is moving with angular velocity omega, velocity of different parts are different. Velocity of different parts are different. If I consider any element which is at a distance x from here and this one, like this one, green one, dx, it's not very much visible, this one. If I take this particular element, then velocity of this part will be omega x. Means the velocity of different parts are different. So here the EMF generated, EMF induced is not same for all. They are moving with a different velocity. So we have to go for integration technique. There are three types of cases. EMF generated is V cross B dot dl. Now in this V can be varying, B can be varying over for a small length. If any of the thing V or B or the angle between V and B is varying, then we have to go for integration. And if both are constant, then we can write directly V cross B dot L. So now here velocity is varying. As the velocity is varying, we have to go for integration technique. So to determine the EMF generated, what I am doing, I am taking an element at a distance x of width dx, this one. Now velocity of this part, this small dx part is omega x. So the EMF across this small part, small element is dE is equal to V cross B. V is omega x. And angle between velocity and magnetic field is 90. So V cross B is omega x into B. Now this omega x cross B is parallel to dx. Parallel or anti-parallel direction we are not seeing this way, we will see later on. Omega x cross B will be along the length of the rod, along the length of the element. So into dx. Now if I use the right hand palm rule number 3 and want to replace it by the equivalent battery, this small element, then velocity this way, magnetic field this way. So thumb you point this way, fingers you point this way, then the normal will come, outward normal to the right palm will come this way. So this particular small part will be replaced by a battery this way. This is dE. It means each and every small part of the rod will be replaced in this way. And these all will be in series. If these all small elements are going to be in series, then the equivalent EMF is equal to integral of dE. And this will give you omega x b dx. Length given L, so 0 to L, omega b L square by 2. And from this particular diagram, it is clear that A is at higher potential than B. So we can write EA minus EB, EMF induced across AB with A at higher potential is omega B L square by. Now if I change this question, a very nice question. Let us say if it is given AB is non-conducting rod. AB is non-conducting rod. And the entire situation remains same. Then what is the EMF induced? Then you remember motional EMF, how the EMF was being generated because of the movement of free electrons. If the non-conducting, no free electrons movement, no accumulation of charges, no EMF will be induced. Then in this particular case, you have to remember the EMF induced will be 0. Very important thing. Motional EMF takes place only in the conducting material, not in the non-conducting material. Take one more question. We have a conducting disc. We have not disc, ring you take. We have a conducting ring of some mass etc. given, and it is rotating about its own axis in a uniform magnetic field. Then for the ring, we have to find the EMF induced between the center and the periphery. A is the point at the center and B is at a point on the periphery. So we have to find EA minus EB. First we are doing for ring. Now if you see, as the ring is rotating, the flux linked with the ring, this particular part, is not changing. It is constant. So the EMF induced between this point and this point will be 0. For the ring, flux is constant. No cutting of flux. So the EMF induced is 0. Now try to see for the disk. Many students ask that we have the trouble, then for this also 0, then for disk also has to be 0. But for disk, it is not the case. Now, if it is disk, means here some material is there. Then what is happening? As this disk is rotating, every part of the rod is cutting the field lines. They are cutting the field lines. Now, as a result of that cutting of field lines, EMF developed between the center and the periphery. Between the center and the periphery, EMF is developing. But if you take the EMF between 2 points on the periphery, it will be 0. I'll explain this point in detail. You see, let us take This is the disc. Now this disc is consisting of some material like this. You can say some rods whose thickness are varying like this. Now as it is rotating, and discs are not only there, here also this will be there like this way, it will be there. Now if it is rotating this way, field lines are going this way, and here the field lines are coming this way. So both are cutting the field. So just now we have seen if a rod is rotating in a uniform magnetic field about one of its ends, EMF induced across its two ends. Now here also you say any one rod, this is the center, this is A, this is B, diametrically opposite. Then from that formula only you can say EMF induced between A and B, C and B, and between C and A you see. Between C and B it will be B omega R square by 2. With which point at in the question I have taken the angular velocity direction reverse. So no problem. Here also same will take. Direction of the map. It is this way. Magnetic, angular velocity is this way. Now, this way means it is having the velocity in this direction. Magnetic field is into the board. So the EMF induced will be in this way. With respect to point C, this way. CV will be. And here the velocity is in this way, magnetic into the board. So the EMF induced will be this is positive, this is negative, this way. So if I want to draw the diagram from A to B, then I have to draw like this. So EMF induced between any two points on the periphery. This is say E, and the value of E we know it will come out to be omega B R square by 2. Then if I am moving from here to here, here to here, minus E plus E, and it will become 0. But when I want to find the EMF induced between center and periphery, then it will be E only. So in this also, whatever doubt you have, when they here also no net cutting of flux or no net changing of flux, then how the EMF is induced? Then in this, EMF induced across the periphery is 0 only. And when we are saying in the Faraday law of electromagnetic induction, EMF is induced in the boundary, in the circuit, that EMF is along the boundary of the circuit, not in the inner part of the circuit. And here, inner part, if you see, between C and A, some positive EMF and some EMF E, and between C and B also, but between 2 points on the periphery, it comes out to be 0. Let's take one more question. We have taken various questions, some question in which the field was varying, some question in which the uh, angle was varying, some questions in which the velocity was varying of different parts. Now here one such question in which the field is non-uniform. A moving conductor is moving in a non-uniform magnet. Consider one infinite long conductor carrying current I, and we have one conducting rod. This is conducting rod AB of length L, which is moving in with velocity V parallel to the length of the wire, and we have to find the EMF induced across AB. We have to find the EMF induced across AB. This is what we have to find. Now in this question, magnetic field at the location, at different location, here, 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 due to the wire is different. This conductor is moving in non-uniform magnetic field. So if it is moving in non-uniform magnetic field, we have to go for the integration technique. Let us say at a distance x, we considered a small element of length dx. This length is dx. Now, magnetic field at this location is, due to the wire, is mu naught I upon 2 pi x. This field is into the paper. Due to the movement of this small element dx in this magnetic field B, a EMF is induced across it, dE equal to VB dx. Mu naught I 2 pi x V dx. It comes with the direction from right hand palm rule number 3. You can say this is the direction. Since all the polarities are going to be same for small elements, they are in series, so the equivalent EMF will come out to be integral of dE, that is mu naught IV upon 2 pi dx by x. X varies from this location to this location, that is A to A plus, and you will get your answer, right? So here, non-uniform magnetic field, moving rotating rod, non-uniform velocity, right? One more question you can take, somewhat similar to this only. Let us say this is the situation. I am not solving it, only telling you how to you can proceed. What is some important points? Infinite long current carrying wire. This distance given to you. This square loop side also given to you. We have to find the flux linked with it. Now, sorry, EMF induced in this particular loop, ABCD. Now, EMF induced in this loop will be 0. Directly you can say. Why? Because here will be some field. This way field is there. So when it is moving with some velocity, it is moving with velocity v, and then we have to find the EMF induced. When it is moving from here, from this side, field lines enter the, but from this side, field lines leave. So the EMF induced in this loop is 0 because there is no net cutting of flux. Because there is no net cutting of flux, that's why EMF induced in this part will be 0. Now here you see one thing. EMF induced in this part will be there. It is very much similar to this part only. So I am saying EMF induced in AB is E. Then it will be like this, E. And the value of this expression for E will be same as the previous. EMF induced for AD will be 0. For AD it will be 0. And for DC again it will be E. And for BC it will be 0. So what is the net EMF induced along the loop? Minus E plus E equal to 0. Actually, with the help of this point, I want to tell if the flux linked with a circuit is 0 or not varying, or no net cutting of flux linked with a circuit is there, then total EMF is 0. But it might be possible that EMF induced in different parts is non-zero. Like here you see EMF induced across this part is non-zero. EMF induced across this part is non-zero. But EMF induced across the whole part will be 0. Right? I hope the concepts are clear to you of the motional EMF.